All right, this is 16.2 of your note packet. When we left 16.1, we had gotten some basic definitions of Bronsted-Lowry acids and bases, of Arrhenius, I should say. But now we're going to look at another definition that's going to allow us to branch out a little bit. We talked about Arrhenius. Now we're going to look at Bronsted-Lowry. Because one of the limitations we have is there are many, many, many more bases besides those which contain hydroxide. And so this definition will allow us to include those particular bases in our definition. A Bronsted-Lowry is not limited to aqueous solution. It involves only the transfer of a hydrogen ion from one substance to another. So let's start with something really simple that you're going to see a lot. A hydrogen ion and water. Now, water has the unshared pair of electrons, so it can snatch up that hydrogen ion and make what's called hydronium ion. Basically, often, in fact, in acid-base chemistry, you may see the acid that you're interested in reacting with water to make the hydronium ion and its conjugate base. This is also written as H3O+. And so chemists use the symbols H+ and H3O+ interchangeably. You'll also see or hear H+ referred to as a proton. I think I probably will do that a lot. So in this case, in the last reaction, we took HCl, we broke it into H+ and Cl-. If, however, I write the same kind of acid-base chemistry, in this case as a gas with water, then I can get H3O+. Notice that now water snatched that proton away, and Cl-, and these are both aqueous. HCl acts as an acid because it donates an H+, and water behaves as a base because it accepts a proton. Do we need that the reactions take place in water? No, we do not. And you're going to see that we will go back and forth using water in the equation and sometimes not in the equation as well. Now, let's look at another kind of equation. What if I have two gases? These are two gases that react to form solid ammonium chloride. So those two gases would be hydrochloric acid and ammonia. These react together to form NH4+ plus Cl-. And this salt here will form smoke. And if you notice, what happened is we've got a transfer of a hydrogen to make this happen. The acid is HCl because it donates. It is a proton donator. And a base is ammonia because it is a proton acceptor. And so the acid-base chemistry happened without any water at all. Now, bases can also react with water. In fact, you usually will put water in the equation for bases. You'll see this. And in this case, remember that this is a new kind of base for you all, and it's same with up here. Remember, the Lewis structure for ammonia looks like this. That unshared pair of electrons can come and snatch up a proton from water. And when it does that, it makes NH4+ plus OH-. And these are both aqueous. NH3 acts as a base, right? Because it accepts the proton from the water to give NH4+, and water behaves as an acid because it donates a proton. So the bottom line is a Bronsted-Lowry acid must have a proton it can donate, and a Bronsted-Lowry base must have a lone pair of electrons that it can use to bind to the hydrogen ion. Okay, now substances can be both. All right, so let's look at the definition of amphoprotic. here. It is a substance that is capable of acting as an acid or a base. Examples include water, the hydrogen carbonate, and the hydrogen sulfate ions. So that is the definition of amphoteric, a substance that is capable is acting as an acid or a base. So now let's kind of put all this together. What we need to do first is look at some chemical reactions and identify what our acids are and what our bases are. Well, we know, looking at here, these are our reactants, these are our products. This begins with hydrogen. That is our acid. Our acid is going to react with our base. Notice that what's happened is that this proton has donated to water to give this nitrite ion and a hydronium ion. So our base is going to be water. Looking at the products from the equation, right? So because remember, we could go the other direction. What we have here now is that we have what's called conjugates, either the conjugate acid or the conjugate base. Now what happens here is that the acid makes the conjugate base. So the acid makes the conjugate base, and the base makes the conjugate acid. And this can be confusing to remember, but we're just going to keep doing it over and over. Let's look at this equation. So if we look at this side, the acid, of course, is water here, and the base is ammonia. Remember that the base is going to make the conjugate acid, and the acid is going to make the conjugate base. Okay. Every acid has a conjugate base formed by removing a proton, and every base has a conjugate acid by adding a proton. Okay, so let's apply this to some examples here. If I look at all of these, I should be able to determine what the conjugates are. The conjugates are the result of, in the case of an acid, donating a proton. So there's donated a proton. Donated, I have two here. I'm only going to donate one. Donate one. Still just donating one. I have one here to donate. And now notice what's happening to the charges, right? I'm losing a positive charge. So I'm 2 minus here. I'm 3 minus here. I'm 1 minus here. 2 minus here. Look at this one. This was positively charged. Now I'm neutral. That's because I'm losing a positive when I do this. And then water is OH minus. Now again, this is a different kind of base. This is like taking this, and you'll see these a lot, ammonia, and I can replace one or all of these hydrogens with something else, and that's what I did here. I replaced one of my hydrogens with a methyl group, but my unshared pair of electrons is still there to pick up my proton, and now that's going to be positively charged. I can also do the same here, picking up a proton. Now if I do this here, SO4 1 minus, because I've added a positive charge. H2 CO3 H2 PO4 minus and H3O plus. So that's some examples of some of the conjugates. So let's look at a amphoteric or a ion that can act as an acid or a base. So we're going to look at bicarbonate. Bicarbonate looks like this. Now, if it reacts with water, it can lose a proton and generate carbonate, or it can gain a proton and make carbonic acid with hydroxide. Okay? And so I can do either of this in that scenario. Now, as far as strengths goes, and this is going to be really important, we're going to talk a lot about acid and base strengths. The stronger the acid, the weaker its conjugate. So the way to remember this is if one of them is strong, they can't both be strong. So if one of them is strong, the other one is weak. If one is weak, the other is strong. Okay? The stronger the base is, the weaker the conjugate acid. Now, remember that when we started, it was back, I think, in like chapter 4, we talked about strong acids and weak acids. So we're going to kind of define that now. Strong acids and weak acids are determined in this way. Strong acids completely dissociate 100%. A weak acid partially dissociates. Now, the way that we're going to denote this is that you will see a single arrow for this one, and you will see a double arrow for this one. So I'm going to stop the video here at S, and we're going to go on and then talk about how we memorize some of these species so that we can go on and use them in some of our acid-base equilibria.